In this video, we'll talk about proof by contradiction. So let's talk about the theory behind contradiction. The whole idea, if we're trying to prove a statement, which in this case we're using H implies C, let's call this statement S. And the idea is, somewhere along the line we suppose H implies C is false. Which means that we would then say, okay, suppose we have H and not C, which is the proper form of a counterexample. And the idea is I walk through the effects and the definitions. I talk about, okay, if this were the case, what would that mean in terms of the original proof? And the idea is, what they'll write in textbooks is you will somehow get S and not S, which is a bit arbitrary, a little bit tough to discern what's going on there, but the idea is if I suppose it's false, the only way it can be false is if some of my original conditions are not met. So in essence, what this does is it eliminates the possibility of a counterexample. So basically, I'm not proving it true, I'm just proving that there's no case to prove it false, or the only way it could be false is for the original statement to be false, which creates a contradiction. So let's go ahead and talk about an example. Sometimes putting one to practice makes a big difference. So if we're looking at a contradiction proof, there's three phases. There's the setup, which is where we look at our hypothesis and we just allow all that stuff to happen. We bring in any definitions we may or may not need, and that's it. So let's go ahead and start that. So let's look at this statement. The product of two rational numbers is rational. So my hypothesis, even if it's not so much clear-cut, I'm going to rewrite this a little bit. The idea is if x and y are both rational, meaning they're members of the rational numbers, that's what this shorthand means, then x times y, the product of the two, is rational. And that might not be so much clear-cut from the original statement, but this is the if-then equivalent of that. If I have two rational numbers and I multiply them, then it's rational. So the idea is I'm going to let that happen. So we'll start our proof. We're going to let x and y both be rational. Now, remember that for a rational number, technically there's two working definitions. There's one with the decimal, where we're talking about a terminating or repeating decimal. That one's a little difficult to work with in a proof. I prefer the one where if a number is rational, then it can be written as a fraction involving only integers. So what this would mean, this is where I'm using the definition of rational. So x can equal a over b, and y can equal some c over d, where a, b, c, and d are all members of the integers. They're whole numbers or negatives of whole numbers. That's what it means to be rational. So I could say this by definition of rational. That's a cold hard fact. That is our setup. We have let our hypothesis happen, and we have used any definitions, we've clarified what it means. Now we move on to our next step, our next phase. So I'm going to scoot this up just a touch. So here's where we make a supposition. That's our second phase. We're going to suppose our statement is false. So suppose x times y is not rational. That would mean that x times y cannot equal, and I'll use another couple letters here, let's say e over f, where e and f are integers. That's what it would mean. If it's irrational, I cannot write it as a fraction involving two integers. There's my supposition. Now I move on to the third phase of contradiction. there's two ways you can go with this. You can build off of your supposition and somehow violate the original, or you can build off of the original and somehow show that this can't be true. The supposition can't be true, I should clarify. So the idea is we're going to build on our original here for this one. We're going to go through and we're going to say, okay, but x times y is equal to a over b times c over d, which is equal to a times c over b times d. That's how we multiply fractions. We go straight across top, straight across the bottom. Now, since we can say, I think we can pretty safely say a times c is a member of the integers. If I multiply an integer by an integer, it's an integer. And then likewise, b times d is also a member of the integers. And I'll put a star on this line because we may have to prove that one later down the line, but for now, I think we can accept that as a result. If I multiply 5 times 5, I'm still going to land as an integer, or vice versa, 5 times a negative 5. So, moving forward, this would tell me, since they're both integers in the numerator and denominator, that x times y has to be rational, which is a contradiction. And when we end a contradiction proof, we have like a double implies arrow against each other. That's kind of like the punctuation for it. And this violates my supposition. That's where we get the proof. I have shown the only way for this to be true is if, or that x times y has to be integers. And it's very possible we didn't need this supposition here, but it does give us a roadmap of what we need to show in order to complete the proof. And that's why I usually teach contradiction first. And it's something that's useful in ways that you have kind of a roadmap to follow. You're going to start with your hypothesis. You're going to use any definitions you may need. You're going to suppose it's false and then somehow show that it can't be false, one way or the other.